Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. I welcome you to the 16th lecture on advanced computer architecture. Today, I will talk about the dynamic branch prediction. Before starting with our discussion onto the dynamic branch prediction, I'll give you a brief review of what we have said up till now. We know that the pipeline data path facilitates overlapping of the execution of instruction to enhance the overall performance of a processor. This overlapping of execution is referred to as the instruction level parallelism. While talking about instruction level parallelism, we observe that the amount of parallelism available within a block of instructions, that is a straight line code, is quite small. Usually, a block consists of 4 to 7 straight line instructions. So this means that the frequency of branches is ranging from 15% to 25% in a program. Now, this amount of branch frequency, in fact, gives rise to large number of control hazards. Therefore, to obtain the performance enhancement, we must give importance to reduce the number of stalls by using different prediction techniques for while talking about the control hazards. This type of parallelism across the iterations of the loops is referred to as the loop level parallelism. We know that there are two largely separable approaches to deal with the instruction level parallelism and to overcome the data as well as the control hazards, and the number of stalls are to be reduced to enhance the overall performance. For this purpose, we said that there are two distinct techniques. These techniques are known as the static techniques and the dynamic techniques. The static techniques rely on the software, that is the compiler, whereas the dynamic techniques, which take care of the data dependency as well as the branches during the execution of a program, and it is taken care of by using some hardware approaches. We discussed two basic techniques for dynamic scheduling known as the scoreboard technique and Tomasello's approach. Then we started our discussion for the control hazards, where for the control hazard we use different prediction techniques. We discussed the branch prediction buffer or branch history table technique by using 1-bit predictor or 2-bit predictor. We also discussed a few limitations of this type of predictor, particularly when there are multiple branches in a program and these branches are correlated. Therefore, in order to deal with this situation, we introduced the concept of correlating predictors. Then, in order to have multiple delivery of instructions, we discussed another technique known as the branch target buffer. However, in the last discussions, we simply introduced these techniques. Therefore, today I will go into the more details of these techniques one by one. We will look into the limitations and the techniques, how we can overcome these limitations while using different techniques. Let us first of all consider the branch prediction technique, where we discussed that the branch prediction technique can employ a branch history table which contains either 1-bit information or 2-bit information. But there are two important problems, or we can say two important questions, which arise when we talk about branch prediction buffer. The first question is, what is the impact of increasing the size of branch prediction buffer on two branches in a program? This means that if within one program there are more than one branches, and we want, or we think that if we will increase the size of the branch prediction buffer, whether it improves the performance or not. As you know that a single predictor predicting a single branch is generally more accurate than is that same predictor serving more than one branches. So, moreover, it is less likely that two branches in a program share a single predictor. Therefore, we can say that under this situation, a single branch predictor, its performance cannot be increased, or the number of mispredictions cannot be reduced by simply increasing the size of the buffer. This we also discussed with the help of a comparator chart, and we found that if we are using 4K entry branch predictor and unlimited entry branch predictor, there is almost no difference in the performance. However, the second question is that how sharing a predictor affects the misprediction, which means that if under certain situations, if we want to share the predictor for more than one branches, then how it will affect the mispredictions, whether the mispredictions will be increased or mispredictions will be decreased or they will remain unchanged. This is explained with the help of example. Here we consider two sequences of branch taken and not taken sharing 1-bit predictor, and we will try to identify the sequence that reduces the misprediction rate or that increases the misprediction rate. For this, let us have a look onto this first sequence. Here, the column B1 and B2 show the branches B1 and B2 respectively. We assume that B1 is always taken and B2 is always not taken. The prediction bit P is initially not taken and it inverts every time mispredicted. The prediction for B1 is not correct for the first time, therefore P is inverted from not taken to taken. Then you can see that the first B2 is therefore also mispredicted and P is inverted again to not taken. Now this time when we invert P once again, it will once again result in misprediction for second B1 and it is inverted again. So in this table you can see that when B1 and B2 are always taken and not taken and they are interleaved, if each would have a separate 1-bit predictor, each would have correctly predicted after the initial misprediction. But when they are using the same predictor, the predictor bit changes its state, therefore the overall accuracy reduces to 0%. However, Now we can have a look into another sequence. In this sequence, the column B1 and B2 show the branches B1 and B2. This time, we are assuming that B1 is taken for first time and the alternatively not taken, then next time it is again taken. So this goes on changing from taken to not taken alternatively. Similarly, B2 is initially not taken and then it alternately changes to taken and not taken. Now, in this particular situation, the prediction bit P is initially not taken and it inverts every time it is mispredicted. The prediction for B1 is not correct for the first time here. Therefore, P is inverted from not taken to taken. Similarly, the first B2 is therefore mispredicted and P is inverted again to not taken, which results in correct prediction for B1. The above table, as you can see from here, it shows that when B1 and B2 both alternate between taken and not taken, the accuracy of one bit predictor improves to 50% as compared to the case where B1 is always taken and B2 is always mistaken in case of our first sequence. So this shows that the sequence of more than one branches and the way they change their behavior, that very much determines whether the misprediction rate will increase or it will decrease when we are ready to share one predictor to deal with two branches. Here you can see that it is clear from this example that a predictor is shared by a set of branch instructions. Then the members of the set of branch instruction may change over the course of execution of long program. Hence, the branch action history changes and predictor is likely to mispredict more often. Now, let us have a look onto the performance and working of correlating branch predictor, which we introduced last time. We have observed that in a program segment like the one which is shown over here, where the first statement, if D is equal to 0, then D is equal to 1, and the second branch is corresponding to if D is equal to 1, then D is equal to 2. It shows that the branch B1 will occur when D is not equal to 0, and branch B2 will occur when B is not equal to 1. So this shows that the branches B1 and B2 are correlated. That is, the prediction of current branch, in this particular example, say branch B2, is affected by the behavior of recently executed branch, in this case, the branch B1. Here, as you can see, that if branch B1 is predicted as taken, then the prediction is correct if B1 is not taken, and it may be mispredicted if initial value of D is not equal to 0. So this problem may be resolved in correlating branch predictor, where we record M most recently branches as taken or not taken in 2 raised to power M branch history tables for either 1-bit predictor, 2-bit predictor, or n-bit predictor. In general, it is written as M, N predictor, which means that record last M branches to select between 2 raised to power M history tables, each with n-bit counter. The n-bit counter means whether it is where n is equal to 1, 2, or have any value, and it determines the 1-bit, 2-bit, or n-bit predictor. So, using this general terminology, we can say that a 2-bit branch history table can be regarded as a 0-2 correlating predictor. Similarly, a 2-bit correlating 2-bit predictor can be written as 2,2 predictor. Now we will have a look into the performance of the correlating predictor with the help of an example. Here, a 1-bit predictor with one correlating bit can be written as 1,1 predictor. Here we have 2 raised to power 1, that is 2 separate prediction bits, that is 2 1-bit branch history tables. One prediction bit is used in the last branch executed was not taken, and the other prediction bit is used if the last branch prediction is taken. These 2 bits are denoted as new prediction when last not taken / new prediction when last taken. For example, the expression T/NT stands for new prediction is taken if previous prediction was not taken, and is not taken if previous prediction was taken. In an NM predictor, the global history of most recent M branches is recorded in an M-bit shift register. Here, each bit records whether the branch was taken or not taken. This you can see for an example of 2,2 correlating predictor shown in this diagram. Here, the buffer is drawn as a 2-dimensional object. Each buffer is 2-bit wide. In reality, they are arranged linearly. You can see over here they are arranged in 4 columns, whereas actually they are part of one array which is arranged linearly. 2,2 branch prediction buffer uses 2-bit global history to choose from among 4 predictors. For each branch address of 4-bit, which determines one of the 16 entries in each row, behavior of recent branches selects between, say, 4 predictors of next branch, updating just that prediction. Indexing is done by concatenation of 4 lower order address bits of the branch word address and 2 global bits to form 6-bit address to select 2-bit prediction for 64 entries in 4 buffers, each of 16 entries. Let us compare the performance of simple 2-bit predictor and 2,2 correlating predictor. Here you can see that in this graph, a simple 2-bit predictor with 4K prediction entries versus 2,2 predictor with 1K entries. Here, if you note that both these predictors have same number of bits, that is 8K, and the 2-bit predictor is shown with unlimited entries. You can see here that 2,2 correlating predictor with 1K entries outperforms in comparison with simple 2-bit predictor with same number of entries as well as with unlimited number of entries. There exists a wide range of correlating predictors. However, the 0,2 and 2,2 correlating predictors are outperforming, and they are most commonly used. Now, with this much discussion on to correlating predictor, we will talk about multi-level branch prediction. The multi-level branch prediction means that if in any program we have nested branching, how we can predict the behavior of these branches so that overall number of stalls are minimized. The standard 2-bit predictor uses only local information, whereas the multi-level branch prediction in fact involves the global information also. Therefore, another concept is used in order to predict the multi-level branch behavior. The predictor used for this purpose is known as the tournament predictor. The tournament predictor works on the principle of adaptivity, which is used to combine the local and global predictors with the help of a selector. Tournament branch predictor uses several levels of branch predictors and an algorithm to select a particular predictor. For example, we can have a 4-state tournament branch predictor which employs 2-bit counter as a selector for a particular state. Here is a state transition diagram for tournament predictor for 2 predictors having a 2-bit saturating counter. This 2-bit saturating counter has 4 states corresponding to which predictor to be used. Here, the saturating state 00 and non-saturating state 01 are assigned to predictor 1, and the saturating state 11 and non-saturating state 10 are assigned to predictor 2. The transition of predictor predicted is specified by correct is equal to 1 and incorrect is equal to 0. This state transition diagram shows that from the saturating state, the counter is incremented whenever predicted predictor is correct and other is incorrect. For example, as you can see in this case, the transition written as 1/0. The counter is decremented when the predicted predictor is incorrect, and for example, over here for the state 0/1. The counter does not change for all other predictions for non-saturating present state. For the saturating state 00, which is assigned to use predictor 1, it increments to the state 01 for predictor 1 when the transition is 1/0, and it decrements to state 11, that is to use predictor 2 for 01. Here you can see that decrement from saturating state 00 to the saturating state 11, it is due to the saturating behavior of the counter. However, you can see over here that for the saturating state 11, which is assigned to use predictor 2, it increments to state 00 for transition 1/0 and it decrements to state 10 for 0/1. So you can see that over here with this tournament predictor, we can determine which particular predictor is to be used when we have multi-level branch instructions. So the performance of this type of predictor is outstanding, and it gives the better performance as compared to the n-bit predictor or the correlating predictor. Now, with this much discussion on to the predictors, we will move on to the discussion onto the performance for multiple instruction delivery. In a high performance pipeline, especially with the multiple issue, it is not sufficient to predict the branches well. Rather, we need to predict and deliver the instructions at the same time. Recently available processors has got 4 to 8 instruction delivery at the same time. However, at this stage, a question arises that what is needed for instruction delivery? We know that it needs the target address. Therefore, for high delivery rate, we need to know the target addresses of more than one branch instructions to be available simultaneously in the buffer. For example, in MIPS 5-stage pipeline, we need to know the address of the next instruction fetch at the end of the current instruction fetch cycle. That is, if 0 branch penalty is needed, we have to know whether the as yet undecoded instruction is branch, and if yes, then what is the next program counter. This is accomplished by introducing a cache that contains the address of the next instruction if branch is taken as well as not taken. This cache is known as a branch target cache or branch target buffer. I introduced to you last time the basic structure of a branch target buffer. Today, we will look into more details the design of a branch target buffer. Here you can see onto this diagram that a branch target buffer consists of 3 fields known as the lookup field, predicted PC field, and prediction state. The lookup field contains the addresses of the known branch instructions predicted as taken. Predicted PC contains the value of the program counter of the fetched instruction predicted taken branch. And the prediction state contains extra prediction state bit. This field is optional and it may or may not be included. The branch target buffer functions as follows. The program counter of the instruction being fetched is matched with the entries available in the lookup field. If the match is found, then the fetching begins immediately. You can note here that we have stored information about only the predictions taken, and we have not included the information corresponding to predicted not taken in the target buffer. Over here in the target buffer predictor, the target address is already available. Therefore, instead of getting the next instruction from the program counter, the next instruction is obtained from the entry available in the corresponding target buffer section. The steps involved in using the branch target buffer at instruction fetch, instruction decode, and execution stage are shown here with the help of this flowchart. Here you can see that in the instruction fetch stage, the program counter of an instruction is compared with the contents of the buffer. If it is found, then the instruction must be a branch instruction predicted taken. Otherwise, it may be a branch predicted not taken or a normal non-branch instruction. So after taking this decision at this stage, in the ID stage, the instruction is decoded, and if in the instruction fetch stage, entry was found in the target buffer as predicted branch, then it begins fetching immediately from the predicted program counter. The second step may be that as a result of the decode, whatsoever is the instruction, it checks the decoded instruction. If it is taken branch, then the branch address is obtained. Whereas in the execution stage, it moves on to the execution stage where it performs one of the four possible functions. One, where in the if stage, that is in the instruction fetch stage, entry was not found in the target buffer, and in the instruction decode stage, if it is found to be taken branch, then it takes one step, and that step is enter branch instruction address and next program counter into branch target buffer. Whereas if it is found to be taken branch, then enter branch instruction address and next program counter into branch target buffer. Otherwise, proceed as normal instruction execution. Whereas at the execution stage, the second possibility is where in the instruction fetch stage, the entry was found in the target buffer, and in the instruction decode stage, if it is found to be taken branch, so this means that it is correctly predicted, therefore it executes normally without star. Otherwise, it is mispredicted, so it kills the fetched instruction, restart the fetching at an other address, and delete entry from the target buffer. If the correctly predicted branch entry is found in the buffer, then there will be no branch penalty. Otherwise, it suffers at least 2 clock cycle delay as misprediction penalty. Here, 1 clock cycle delay is for fetching the wrong instruction, and 1 clock cycle is to restart the fetch. In practice, this penalty could be more as the branch target buffer is also to be updated. We can look into the performance of branch target buffer with the help of an example now. Over here, let us consider the following table, which shows that the penalty cycles for all possible combinations of branches, assuming only taken branches are stored in branch target buffer. Here, if the instruction is in the buffer and it has been predicted as taken, and if the actual branch has been taken, this means there is no penalty. Whereas if the actual branch is not taken, then a penalty of 2 cycles will be there. Whereas if the instruction is not available in the buffer, so in this case, if the actual branch is taken, then there is a penalty of 2 cycles, and if it is not taken, then there is no penalty. Now in this example, if we assume that the prediction accuracy for instruction in the buffer is 90%. The hit rate of branches predicted taken is 95%. Then let us determine the total branch penalty for branch target buffer. Let us have a look onto this calculation over here. We can compute the penalty by looking at the probability of two events. Number one, branch predicted taken, but it ends up not taken. So this is equal to percentage buffer hit rate multiplied by percent incorrect prediction. And for this example, it is equal to 0.95 multiplied by 0.1. 0.95 is for the hit rate and 0.1 is for incorrect prediction of 10%, where correct prediction is 90%. So it results in a value which is equal to 0.095. The second case is that branch is taken but not found in the buffer. So this is in fact equivalent to the percent incorrect prediction, and this value is equal to 0.1, as the incorrect prediction is only 10%. The penalty in both the cases is 2 cycles. Therefore, the total penalty is equal to the penalty due to branch predicted taken but ends up with not taken, and the branch is taken but is not found in the buffer. So this value is equal to 0.095 plus 0.1, which is equal to 0.195 multiplied by 2, and it results in a value which is equal to 0.39. So this shows that the branch target buffer gives us good performance if it is predicted correctly. Now let us consider another example where we will consider a branch target buffer implemented for conditional branching only for pipeline processors. Here we assume that the missed prediction penalty is equal to 4 cycles. Buffer missed penalty is equal to 3 cycles. We assume the hit rate and accuracy both individually equal to 90%, and the branch frequency is equal to 15%. This means that in a program, the branch frequency is 15%. So for this example, we have to see how much faster is the processor with branch target buffer as compared to processor without target buffer. If we have fixed branch penalty of 2 cycles and base clock cycles per instruction without branch stall of 1 cycle. In order to solve this problem, we have to define the speed up with branch target buffer and without branch target buffer. For this purpose, let us see this expression where speed up is defined as it is equal to the clock cycles per instructions for no branch target buffer divided by the clock cycles per instruction with branch target buffer. The clock cycles per instructions without any branch target buffers is equal to the base clock cycles per instruction plus the stalls for no branch target buffer, whereas the clock cycles per instruction with branch target buffer is equal to the base clock cycles per instructions and the stalls with branch target buffer. Whereas the number of stalls for with a branch target buffer or without a branch target buffer can be defined as it is equal to the sum of the product of the frequency of the event multiplied by the penalty. From the frequency, we mean that whether it is corresponding to no branch or it is corresponding to with branch prediction buffer. So let us see how we can solve this problem by using this definition. Here you can see that at the first step, we find out the stalls with no branch target buffer. And as we have already said, that the penalty when there is no branch target buffer is equal to 2, and its frequency is 15%. Therefore, the number of stalls with no branch target buffer is equal to 0.15 multiplied by 2, which is equal to 0.30. Now, the second step is to find the stalls with branch target buffer. In this particular case, we have to consider each output from the branch target buffer. There are 3 different possible situations which we are going to consider one by one. Here, the first situation is that the branch misses the branch target buffer. This situation is one where the frequency is 15% multiplied by 0.1, which is 10%, and it results in a value which is equal to 0.015. In this particular situation, the penalty is equal to 3. Therefore, the stalls are equal to the frequency multiplied by penalty, which is equal to 0.045. The second case is when the branch can hit and correctly predict it. Here, the frequency is equal to 15%, hit is 90%, and predicted is also 90%. This results in a value of 12.1%, or it is equal to 0.121. The penalty as well as stalls in this case is equal to 0. Therefore, the net stall value is equal to 0. The third situation is when the branch can hit but incorrectly predicted. In this particular case, the frequency is 15% multiplied by 90% for hit and 10% for mispredicted. It results in a value which is equal to 1.3% or 0.013. However, in this case, the penalty is 4 cycles. Therefore, the number of stalls is equal to 0.052. Combining all these 3 stalls, it gives us the total number of stalls for with branch prediction buffer cases, that is equal to 0.045 plus 0 plus 0.052, and it is equal to 0.097. Now, with this much information, we can compute the speed up, which is equal to the clock cycles per instruction for the base plus the stalls, and it is stalls for no branch prediction buffer, and its value is equal to 1 plus 0.3, whereas it is divided by the base clock cycles per instructions plus the stalls for branch predicted buffer, which is equal to 1 plus 0.097. So this shows that by adding the branch prediction buffer, it makes the pipeline faster by 20% for this example. So, however, over here we can see that there are certain ways in order to improve the performance of the branch target buffer. The one possible variation in the branch target buffer for having improvement is to store one or more target instructions instead of the target instructions address. We know this thing that the target instruction itself, if it is available in the branch target buffer, then instead of fetching the instruction from the cache, the instruction will be obtained directly from the branch target buffer, and it will enhance the overall performance of the system. Now, with this much discussion, we can conclude that the correlating branch predictor is one which considers the behavior of recently executed branches onto the current branch. We found that this problem can be resolved easily by recording in a branch history table and most recently executed branches as taken or not taken. And this means that we make 2 raised to power m branch history tables. And these branch history tables are made for n-bit predictor, where n may be 1, 2, or any higher number. However, the most commonly used value of n is 1 or 2. Then we found that the correlating predictor having a value of 0, 2 or 2, 2 are most commonly used predictors, whereas higher values such as 12, 1 or so, they are very rarely used in very specialized cases. Then we talked about the tournament predictor, where we found that how multi-level branch instructions can be taken care of, and we can use more than one predictors, and these predictors are selected by using either 2-bit counter, 2-bit saturating counter, or some other higher value of saturating counter if more higher performance is needed. Then we discussed the branch target buffer and its use for multiple issues. And at the end, we discussed the improvements which can be made in the branch target buffer by including the branch instruction instead of including the value of the branch target address. So with this much discussion about different types of predictors, we have in fact covered almost all topics related to the enhancement of the performance by removing or minimizing the hazards. So first we discussed the data hazards, then we discussed the control hazards. Now today I will stop my discussion at this stage, and from next time we will discuss the instruction level parallelism for multiple issues. Till then, Allah Hafiz.